Hello, Dan here from howtomechatronics.com. In this video, we will learn how to build an Arduino-based SCARA robot. I will show you the entire process of building it, starting from designing the robot to developing our own graphic user interface for controlling it. The robot has 4 degrees of freedom and is driven by 4 NEMA 17 stepper motors. Additionally, it has a small servo motor for controlling the end effector or the robot gripper in this case. The brain of this SCARA robot is an Arduino Uno board, which is paired with a CNC shield and 4 A4988 stepper drivers for controlling the motors. Using the processing development environment, I made a graphic user interface which features both forward and inverse kinematics control. With the forward kinematics, we can manually move each robot joint in order to get to the desired position. Using the sliders on the left side, we can set the angle of each joint. The final position of the end effector, the X, Y and Z values, are calculated and printed on the right side of the screen. On the other hand, using inverse kinematics, we can set the desired position of the end effector and the program will automatically calculate the angles for each joint in order the robot to get to that desired position. I actually made the program in a way that we can use both methods at the same time on the same screen. The angles of the joints, as well as the X, Y and Z values of the end effector, are connected and always present on the screen. Of course, the robot can also operate automatically. Using the Save button on the program, we can save each movement or position of the robot. Then, when we press the Run button, the robot will execute the stored movements in a loop, from the first one to the last one, over and over again. We can also adjust the speed of movement and the acceleration from the user interface. Okay, so to begin with, let's take a look at the 3D model. I designed this SCARA robot using 3D Experience SolidWorks, which are actually the sponsor of this video. 3D Experience SolidWorks is basically SolidWorks with cloud capabilities which we get through the 3D Experience platform. Everything works through the cloud, so you or anyone from your team can have access to the data or the models at any time from anywhere in the world. The 3D Experience platform also includes many useful productivity and management apps. For example, the Project Planner is a great way to organize your tasks, set deadlines and keep track of your progress. With the 3D Markup app, you can view, explore and take notes of the models from any device, like a notebook, tablet or even a smartphone. There's also a separate cloud-based 3D modeler called SolidWorks X Design that runs inside your browser. It can be used in conjunction with SolidWorks or on its own, and it's great for modeling anywhere, anytime and on any device. So big thanks to SolidWorks for sponsoring educational content like this. If you would like to know more about 3D Experience SolidWorks, there is a link in the video description so you can check it out. Okay, so let's go back to the model and explain how I came up with this design. My goal for the robot was most of the parts to be 3D printed. So everything you see here can be 3D printed, even on a 3D printer with smaller printing bed. The GT2 pulleys are also 3D printable. I used parametric design to make them, so if needed, we can easily change their sizes. We just have to change the number of teeth and all dimensions will automatically update to make the pulley the proper size. For the first joint, we have 20:1 reduction ratio achieved in 2 stages with these custom designed pulleys. The 2 GT2 belts I use here are closed loop with 200 mm and 300 mm length. The robot joints are composed of 2 thrust bearings and 1 radial bearing. For the second joint, we have 16:1 reduction ratio achieved in the same way, and the third joint has 4:1 reduction ratio with just a single stage reduction. The joints are hollow, so we can use that to pass through the wires from the motors and the micro switches. For each of the belts, there are slots and we can attach idler pulleys for tensioning them. The robot gripper is driven by an MG99 6R servo motor, and we can easily change the gripper ends to achieve different grip sizes. The Z-axis of the robot is driven by an 8mm lead screw, while the whole arm assembly slides on 4 10mm smooth rods and linear ball bearings. The height of the robot simply depends on the length of the smooth rods, which in this case are 40 cm. Okay, so now we can move on with 3D printing the parts. You can find and download the 3D model as well as the STL files which are used for 3D printing on the website article. The link is in the video description. I used my Creality CR10 3D printer for printing all of the parts, which is a really great 3D printer with an affordable price. As I mentioned, the parts are designed to fit on a smaller 3D printer as well, for example the Ender 3, so I will put links to these 3D printers in the video description in case you want to check them out. For most of the parts I used PLA Plus material, the blue one, as well as normal PLA for the pulleys and the gripper. It took me around 120 hours to print all of the parts at 60mm per second printing speed. The base was the biggest part to print, which took around 32 hours. However, if we increase the printing speed, we can definitely print the parts faster. Here are all of the 3D printed parts. Just a quick note here that I printed all of them with enabled horizontal expansion of -0.1mm in the slicing software. This enables the parts to have more accurate dimensions and fit better with the other mechanical parts like the bearings, the rods and the bolts. We start the assembly with the base. Here, first we need to install a radial ball bearing with 35mm inner and 47mm outer diameter. Then it goes the first truss bearing, which has 40mm inner and 60mm outer diameter. This bearing will sit between the pulley and the base. On the other side of the base, we use another truss bearing of the same size together with the joint coupler. Then we can couple the pulley and the upper part using 4 M4 bolts with 55mm length. We need to use self-locking nuts here and tighten them appropriately so the joint is sturdy while being able to freely rotate. Next, we need to install the middle pulley. This pulley is paired with the joint pulley with a 300mm GT2 belt. For installing this pulley, we are using two 608 ball bearings, one on the top and the other at the bottom side of the base. Then, using 45mm M8 bolt, a washer and a self-locking nut, we can secure the pulley in place. Next, we need to install the stepper motor for the first joint. The stepper will be paired with the middle pulley with a 200mm belt. For securing it to the base, we use 4 M3 bolts. Before tightening the bolts, we need to stretch the belt as much as we can. Just a quick note here that I actually replaced the M8 bolt for the middle pulley with its head at the bottom so that it can fit within the base. At this point we should check whether the belts are tight enough. If not, we can use some idler pulleys to tighten them better. Here I'm using a 35mm M5 bolt and some nuts to make the tightening pulley. It can be attached on the slots on both sides of the belt, and so we can tighten the belt as much as we want. With this, the first joint is completed. I moved on with installing the micro switch for the first joint. Before securing it in place, I already soldered the wires to it, as it's a bit tight here to do that after. We need a 20mm M3 bolt and a nut to secure the micro switch in place. The joint coupler passes so close to the switch that I ended up using only one bolt for securing the switch. On the other hole, I just inserted a shorter bolt and glued it at the bottom side. That way the switch is secure enough and can work properly. Next, we can start assembling the Z-axis. First, on top of the joint coupler, we need to secure the Z-axis bottom plate part. On top of it, we can secure the 4 clamps for the smooth rods. Then we can insert the smooth rods in place. They should fit tightly and go all the way down to the joint coupler part. We can then tighten the rods with the clamps with some M4 bolts and nuts. At this point we also need to insert the bearing for the lead screw. To finish this section, we can just slide in a simple cover which will hide everything and give cleaner look to the robot. Next we can move on with assembling the first arm of the robot. The arm will be made out of two parts bolted together. The first part is where we need to install the linear bearings which will slide through the smooth rods. Inserting them in place can be a bit hard because they need to fit quite tight. Actually, this depends on how accurate your printer can print the parts. Therefore, I suggest using the horizontal expansion feature when printing the parts and adjust it according to your printer. In my case, I couldn't fit two of the bearings to go all the way down, but that's not a big deal. Okay, so now we can pair the two parts of the arm together. For that purpose, we will use four 25mm M5 bolts. It's a bit tight here when securing the nuts, but I will modify a little bit the model so you can have better access. Next we can install the second stepper motor. Here I will use a 3D printed GT2 pulley with 20 teeth. I made this pulley using the parametric design I mentioned earlier and it works quite well. Here we also need to secure the lead screw nut in place. Next we can install the belts and the pulleys for the second joint. Here we need one belt with 400mm and one with 300mm length. The procedure for installing them is pretty much the same as explained for the first joint. Here for the second joint and the third one we actually use smaller bearings compared to the first one. The radial bearing has 30mm inner and 42mm outer diameter, and the truss bearing has 35mm inner and 52mm outer diameter. Before installing the second joint coupler, we need to insert 6 20mm M4 bolts in the hexagon slots. They will serve for attaching the second arm to the joint. If needed, for tensioning the belts, we can use the same method as explained earlier with the idler pulleys. Finally, I secured the second micro switch in place and the arm number 1 assembly was completed. I continued with attaching the second arm to the joint coupler. Here we use those bolts in the joint coupler that we installed previously to secure the upper part of the second arm. At this point I wanted to test how much backlash the joints had. Sure, I expected some backlash due to the belts, but there was actually way more play between the two parts of the joints. I noticed that the problem was that the holes where the bolts go are slightly bigger than the bolts themselves. In order to solve this problem, we need tighter fit between the bolts and the holes. So in my case I expanded the holes using 4.5mm drill and used M5 bolts instead of the M4 bolts for securing the two parts of the joint together. However, I will update the 3D model so that the holes are 3.5mm and so you can use the M4 bolts to join the two parts together. I also went back to the first joint and did the same thing. Now the play in the joints is almost gone except for the small backlash that we get from the belts. Alright, so now we can continue with assembling the second arm. Here first we need to install the stepper motor for the third joint. I'm using a smaller stepper motor in this case so that the arm is a bit lighter. Still, it's a NEMA 17 stepper motor but with shorter 24cm length. Again, we have the same procedure for installing the belts and the pulley for the third joint, except that here we use just a single stage reduction with a 400mm belt. Next, before attaching this lower part of the arm to the upper part, we need to connect the motor and the micro switch and pass their wires through the second joint. At this point we also need to insert the wires for the end effector. In my case I inserted a 4 wires cable from a stepper motor, which I will use for driving the servo motor for my gripper, which requires 3 wires. Next we need to insert M4 nuts in the slots of the upper arm, which will serve for securing the lower part to it. Right before merging them, we should pass the wires under these hooks so they stay away from the moving parts. The wires coming out of the second joint can actually get caught by the nuts of the pulley, so therefore I made a simple wire holder to hold the wires away from the nuts. We should arrange the wires to pass on one side of the arm to avoid contact with the moving parts. Finally, we can insert the cover of the first arm. The cover is secured to the arm with a snap fit joint. With this, the robot arm assembly is completed. So next we can insert this whole assembly to the Z-axis rods. Then we need to prepare the Z-axis top plate which will hold the upper ends of the rods. Here first we can install the microswitch for the Z-axis and attach the 4 clamps to the plate. Before putting the top plate in place, first I inserted a simple cover, just like the one below, to hide the clamps, the bolts and the microswitch. Then we can insert and tighten the top plate to the rods using the clamps. Next we need to insert the lead screw in place. The one that I had was a bit longer, so I cut it to 38 cm using a metal handsaw. Next we can attach the fourth stepper motor in place. Here we need to use 5 to 8 mm shaft coupler for connecting the motor to the lead screw. Finally, we can pass the wires through the cover and secure it to the top plate using 2 bolts. Okay, so next we can do some cable management. I used cable sleeves for putting the wires together and clear the mess. I also used some zip ties for that purpose. Before putting the wires in the cable sleeves, it's a good idea to mark each of them so you don't connect anything wrong. What's left now is to make the end effector of the robot. We can actually make and attach any kind of end effector to the robot. I chose to make a simple gripper which is driven by an AMG 99 6R servo motor. The gripper is based on 2 6mm rods on which the 2 sides slide. These 2 sliding slides are connected to the servo with a servo horn, some 3D printed links and M3 bolts and nuts. I used M3 bolts and nuts for the whole gripper assembly. You can actually find a complete list of bolts and nuts required for this project on the website article. The space for securing the bolts and the nuts here is quite tight, so you need some nerves for assembling some of these parts. Though what's good about this design is that we can easily change the gripper ends. They can be wider or narrower, or they can have a specific shape. We can attach the gripper to the robot arm using some M4 bolts and nuts. Finally, we can connect the servo motor to the wires that we installed previously. And that's it, our SCARA robot is completely assembled. What's left now is to connect the electronics components of this project. So we will use an Arduino Uno board in combination with a CNC shield and 4 A4988 stepper drivers. Although it's a robot and it seems more complicated, that's all electronics we need for this project. It's worth noting though that instead of Arduino Uno, we could also use an Arduino Mega in combination with a RAM's 3D printer controller board. Nevertheless, I 3D printed a case for the Arduino Uno, which can be easily attached to the base of the robot. I will use quarter step resolution for driving the steppers, so I placed some jumpers in the appropriate pins. Now we can connect the stepper motors and the micro switches to the CNC shield. Here's the circuit diagram of this project and how everything needs to be connected. For powering the robot, we need 12 volts power supply, capable of providing minimum of 4 amps, but I would suggest 12 volts 6 amps power supply. Of course, this depends on how the stepper driver's current limitation is set, and I would suggest to set it at lowest level possible. At the end, I squeezed all of the wires in the case while trying to leave the driver's heatsinks free and added the cover to it. The SCARA robot is now completed, and what we need to do next is to secure the base to something. For that purpose, I will use 20mm thick piece of wood. At the bottom side of the robot base we have 12 holes available for securing it. So I printed a drawing of the robot base and used it to make the holes in the wood. At the bottom side I countersunk them, as I will use flathead bolts so they are flush with the wood surface. I inserted M4 nuts in the base slots and then secured the wood base to the robot base. Now ideally, in order to fix the robot in place, we could bolt it to the table, or simply I will use clamps for that purpose. So that's it, our SCARA robot is now completely done. What's left in this video though is to take a look how the robot works. There are two methods for controlling robots in terms of positioning and orientation, and that's using forward or inverse kinematics. Forward kinematics is used when we need to find the position and orientation of the end effector from the given joint angles. On the other hand, inverse kinematics is used when we need to find the joint angles for a given position of the end effector. This method makes more sense in robotics, as most of the time we want the robot to position its tool to a particular location or particular x, y and z coordinates. With inverse kinematics we can calculate the joint angles according to the given coordinates. The equations that I will use for both the forward and inverse kinematics come from trigonometry rules and formulas. You can find more details how we get these equations on the website article. Here's how these equations look in a code, written in the processing development environment. So with forward kinematics, we calculate the x and y values of the end effector according to the set joint angles of the robot's arm, θ1 and θ2, as well as their lengths L1 and L2. On the other hand, with inverse kinematics, we calculate the joint angles θ2 and θ1 according to the given position or the x and y coordinates. Depending in which quadrant the position is set to, we make some adjustments to the joint angles with these if statements. For this configuration of the robot, we are actually calculating inverse kinematics with just two links. The third angle, which I called phi, is used for setting the orientation of the gripper. The graphic user interface is made using the Control P5 library for the processing IDE. With this library we can easily create buttons, sliders, text fields and so on. For example, we use the sliders on the left side to control the joint angles, and using the text fields we enter the position where we want our robot to go. With each action we take here with the program, we send data to the Arduino through the serial port. This data includes the joint angles, the gripper value, speed and acceleration values, and indicators for knowing whether we have clicked the save or the run buttons. All this data comes as a single string at the Arduino. So here first we need to extract the data from the string and put it into separate variables. Now with these variables we can take actions with the robot. For example, if we press the save button, we store the current joint angles values in a separate array. If we click the run button, we execute the stored steps, and so on. For controlling the stepper motors, I use the Excel stepper library. Although this is a great library for controlling multiple steppers at the same time, it has some limitations when it comes for controlling a robot like this. When controlling multiple steppers, the library cannot implement acceleration and deceleration, which are important for smoother operation of the robot. I still managed to implement acceleration and deceleration with this library, but they are not as smooth as I wanted to be. Nevertheless, you can find more details about this, as well as the full code with comments explaining what each line does on the website article. The link is in the video description. So finally, once we upload the code to the Arduino, we can run the processing program, connect the power, and the robot will start moving to its home position. From there on we can do whatever we want with it. We can play around manually or set it to work automatically. Of course, we could also attach any kind of end effector and make cool stuff with it. For example, we can even attach a 3D printer hot end to the robot and so make the robot a 3D printer, or attach a laser head and make it a laser cutter. I do plan to try these two ideas, so make sure you subscribe to my channel so you don't miss them in some of my future videos. Before this video ends, I would like to give you a few more notes about this project. I found the robot to be not as rigid as I expected. The problem is that almost the entire robot, the Z-axis and the arms are supported only by the first joint. The whole weight and the inertial forces generated when moving can make quite a stress to the base where the first joint is located, and as it's just a plastic, it tends to bend a little bit. Also, these belts are not backlash free, so we reduce the robot rigidity with that too. However, I think the overall project is good enough so you can learn how SCARA robots work and give you the courage to build one for yourself. Thanks for watching, and for more tutorials and projects, visit howtomechatronics.com.